2 is due on Wednesday. I'll be around a little bit after class today, so it's not a regularly scheduled office hour, but you have questions, that would be one time to ask, or I'll have office hours tomorrow. There's a mix of computing and then doing things just with numerical calculations, with implementation. And today we're going to talk about confidence intervals as a way of doing inference for a mean or a proportion or some parameter. And then Bootstrap is a way to get standard errors for use in those confidence intervals. So, without further ado, 5.1 is a section that talks about confidence intervals. In chapter intervals. In chapter 4, we talked about the sampling distribution of a statistic. And now we want to turn that into a statement about where we think an average or a proportion or something is. So we're going to use it for that purpose. And so if we have a population, and then it has some type of parameter, this might be the average mu. It could be any number of things, just kind of generically a parameter theta. And then we're going to take a sample and have data. And we usually calculate based on that data some summary, and we call that a statistic. And then some form of that, some function of the data gives us an estimate of that. So maybe this is called even an estimator, or a prescription for how do you go about estimating mu. What's the rule? What do you do once you get it? And so X bar is the typical thing there, but of course we might be doing something else, and we'll see different varieties. And generically, we put a little hat on it. A little caret thing, meaning theta hat, or the estimate of theta. And then we want to go back the other way. We want to do our statistical inference and say something over here about the population. And so we're going to try to answer the question, where is mu, where is theta? And our estimator is going to be a good guess, but we want to express uncertainty about that. How accurately do we know that? That's the way this confidence interval. And so a confidence interval is an interval on the real line where you think the parameter is. Where you think the parameter is located. And so shorter intervals are better. So it's better to have a very precise statement if you can make it work out. But at the same time, we want a high probability that this interval actually contains the real interval. If I just say every interval, everything is 5, well, sometimes that might be true, but that's totally precise, but pretty much useless for everything, right? So shorter intervals are better, but we need, I could say, but you need a high level of accuracy. We need a high level of accuracy. And that's where we have our degree of confidence that our interval actually covers. And we usually aim for 90%, 95%, maybe even 99% confidence. So we're going to look at how do you get this interval from the data beyond just the point estimate that says where you think it, can you best guess. your estimator, where that puts that, how do you turn it into an interval? And it has to do with the sampling distribution that we've been looking at. Right? The more spread out the sampling distribution, we have to make our intervals wider. We have a large sample, and we have a very narrow sampling distribution. We're going to have a very precise interval. So the sampling distribution critically helps determine how wide we can make our interval and still have a high level of coverage, right? So to motivate this, suppose a population is normally distributed so that our measurements look like they come from this bell-shaped distribution. I'll call these x's. Right? So our measurements look like this, and they're generally centered about mu with some standard deviation. And we can suppose that we know that standard deviation sigma, and we take independent observations. Then it turns out that the sample average x bar also is normally distributed. It's distributed as some normal, mean is at mu. It's centered at mu, and the standard deviation is sigma over the square root of n. Right? So it gets more precise. And if we let z be our kind of a standardized version, z-scored, right? Subtract the mean, divide by this standard deviation of x bar or standard error. Right? This thing, this little tilde, kind of a shorthand in all the statistical probability literature for distributed as, and it has that probability distribution, is like a standard normal. So that would be a distribution of z here that's centered at 0, and then we know a lot about its probability structure. We know what, yes?
Just in the upper parentheses, that's theta, theta over square root of n.
Sigma, so
or sigma,
yeah, sigma over the square root of n.
But it looks like a k there.
Yeah, it kind of looks like a funny k, doesn't it? Square root of n.
Sigma.
And I don't know, over time I've gotten the habit of making that maybe a little extra little thing in there for square roots. But anyway, it would be this standard normal. So we can say exactly for a standard normal, what values we need to cut off, say, a 95% central area. For a standard normal, if we make them symmetric, they're going to be as narrow as possible. Right? You can get 95% by sliding it over this way, but because this tail is much smaller than this, you have to make it go out here faster as you go this way. But if it's symmetric, it's as short as possible around that. Right? And in particular, we can say that there's a 95% probability that a random value of z is between negative 1.96 and positive 1.96. So the positive probability, negative 1.96 is less than or equal to our standard normal random variable 1.96 is 95%. And you could choose those cutoffs to be 90%, 98%, 99%, whatever you want. And the higher probability is going to make wider intervals, and we'll make them symmetric. Right? But under that other statement, right, the z-score of our x bar is also normal. Right? So we can plug it in there, and the statement will be true. X bar minus mu, and then sigma over the square root of n. 0.95. So that's true, right? Because this thing has a standard normal random variable, so the cutoffs have to be the same. And if you multiply everything inside of here by sigma over square root of n, those equations don't change direction. It all should still be true. So it should be that the probability that negative 1.96, right, sigma over the square root of n is less than or equal to x bar minus mu is less than or equal to 1.96 sigma over square root of n. So that should also be 95%. And now what we'll do is add mu to everything and also subtract x bar. We're going to kind of isolate mu in these equations. So you can think about it as taking, this is one equation here, right? So if you add mu to both sides, mu will be over here. If you add this to both sides, right, then it'll be over here. And anyway, and we're going to do the same thing over here to isolate mu, and then put those two things together. And so a little bit of work, right? And we can get x bar minus 1.96 sigma over the square root of n is less than or equal to mu. Right? So if we add mu to this side and then subtract this from both sides, we would get that equation. And if we operate on this other side, right, we would x bar plus 1.96 sigma over the square root of n. And that's not, the probability hasn't changed. We just manipulated symbols inside and then ended up with two equations we can mash together, right? And so we end up with our parameter isolated. For now, we're pretending that we know sigma. And we get two values that if you knew sigma, you could compute. You could compute this value and you can compute this value. So we call this interval, defined by those things, the 95% confidence interval for mu. So I'll write that out on the next page in just a minute. But so it's manipulating these probability symbols that we get this type of interval. Right? So we say then a 95% confidence interval, a little CI abbreviation there, for mu. We always do an interval to tell us where a parameter is. For that parameter is x bar minus the 1.96 sigma over the square root of n, and x bar plus 1.96 sigma over the square root of n. Right? If we knew sigma. Right? And so the idea is that this gives us one interval, and maybe this interval contains mu. We think of mu as a constant. The parameter as a constant. Right? It describes the entire population or some theoretical average. And so we have this value of mu, if it's drawn here, and we get a data point x bar, and then we're going to put this interval on it, and the width of the interval is going to be determined by this thing like standard error times a multiplier, and we hope that interval covers. Yes?
Before there were less than or equal to signs, this is a closed interval or an open interval?
Well, it could be thought of really either way. So if it's really continuous measurements, right, and you average together, an appreciable number of things, then the chance that it will be exactly that any particular value is basically zero under probability. And there's a lot of things that go on in studies. There's measurement error, people don't report, some missing data, parts of the population not covered. And so in anything like that, even no matter how precise you would get it, there's a little bit of uncertainty where it is. But in the ideal conditions, that you have a good study, good measurement, good participation. So mathematically, it might be open or closed. I'm writing this as, I'm thinking of it as inclusive. So I could, go out with square brackets if we thought it could be actually that last point. But the probability of a single point under a normal would be zero. But anyway, that would give us the interval. We think that describes it, right? In a different sample, we might have randomly ended up with an X bar here. We're going to put an interval on that and so on. Every once in a while, we're going to get an X bar just by chance. That's unusual. Right? We get a surplus of large or very large numbers, and so it ends up out here. So we stretch our interval, right, and it just misses. And the idea of this is that about 95% of intervals should cover. The intervals really are random, right? Because you get a random sample and that gives you X bar, and that's, boom, that's the center of the interval, and so it either does or doesn't. Some don't, but we make this, you know, we can't make things cover 100%, right? 100%, we just have to use the whole real line, which would be no use. 99.9% is going to be, that's going to be great coverage, but those intervals are going to be pretty wide, right? To get under 99.9% of the coverage, I don't know, it's going to be plus or minus 3 standard errors. So it's going to be, you know, a little bit wider on each of these things. Well, if you have a huge amount of data, you could do that, and it still might be useful. But for most things, we keep it at about 95% or something like that. Right? That's where this one illustration of the idea of this interval. Right? And if we knew sigma, and it was normal, we could do this. But most of the time, we don't know sigma, and we don't know a probability distribution. So instead, we're going to use this bootstrap idea to get at the standard error, and we're going to use bootstrap to get at another way of getting an interval. Right? But any questions about this thing? So bootstrap, right? So instead of making assumptions about the population, bootstrap idea. So we have our population, and we take a sample, right, and we're taking X bar. So if you could take, say, 1,000 different samples of size n, we could do this a whole bunch of times. If we could take the population and take it, this is the first one, we could take another one, we could take a third sample. If we could do this, 1,000 times, we could make a histogram of the X bars, and that would show us the sampling distribution. You could see, if you give me 1,000 different random samples, I could see how variable they are, what's the average of X bar across 1,000 samples, and so on. But you're not going to do that. Instead of that, you're going to, just see one number in there. You're going to see only one sample. That's not the way it's done. So instead of doing that, we can't do this. That's not feasible. So we're going to take our sample points, x1, x2, xn points, and what did I call it? We're going to do an approximation to the population. Maybe call that population with a little star on it, kind of a pseudo population. And we're going to base that on our data, so it looks like our data, whether it's skew or has outliers or whatever it is, right? And then we're going to take samples from this one. And these, instead of being ordinary samples, are going to be called bootstrap samples. And if we put stars on those, we're going to do this in a way so that we can do a whole bunch of these. X bar 1,000 stars. Right? And then we're going to look at the distribution of these X bar stars. And this, if we do this in a reusable way, that this distribution of X bars from our approximation to the population should look like the distribution of X bars we would have seen had this actually been feasible. Right? And so there was a German or Austrian story of a Baron Munchausen that picked himself up, you know, he got stuck down in deep holes and caverns, and to get himself out, he picked himself up by his own bootstraps and flew out of the cavern and things like that. So when back in the 60s or 70s, when people were describing, figuring out the mathematics of this, and there is some deeper mathematics that shows why this works in many samples, many different samples from different types of populations. So that this is the way we do it does become a reasonable approximation to the population, and so this becomes a sampling procedure analogous to what's over there. So these, you know, it should match it up pretty well, right? And so how do we do that exactly? So we have our sample of data, our one sample. We are going to treat this like it's the population in a way, or representative of the population. We're going to pick n times from our sample with replacement. And those n values we pick, we're going to call x1 star, x2 star, up to xn star. Right? That's our bootstrap sample, a bootstrap sample of n values. And then based on these, we're going to calculate our statistic, whatever it may be. If we're dealing with x bar, we're going to calculate x bar star. Right? And so all of that done is going to be one bootstrap sample. So we're going to do this independently a whole bunch of times. Say capital B equals about 1,000 times. And this is really why I started using B in any coding I do for the number of indexes, because it's the new number of bootstrap samples. Right? This aspect of picking with replacement, well, what happens if we pick n times from our sample without replacement? If you picked once and then can't pick again, right? And then you pick a second one from what's left over, and then you have to pick again and can't pick from those two. If you pick n times from this without replacement, you're just going to get the same numbers. Like each time you eliminate one, but you have to pick another one, and eventually you just run out. With replacement, you pick one of these, and then they all are back again in the pool, as if it's still the population, and you pick again. Right? It's as if the population is kind of equal 1 over n % of the fraction of the population is at each of these observed values. So it's kind of like a population that way. So you could repeat x1 2 times or 3 times. You can repeat both x1 and x2 multiple times. You can omit x3, it might not be in the sample, right? So that it gives a little bit of variation. Very much similar to like the variation if you picked another random sample from the population. It might concentrate more on parts of it and less on others. Right? I think of this as working better if the sample size n is not really small, right? Because if it's really small, then you only have a little bit of the population. There's some modifications of this simple strategy that kind of smooth it out or try to fit a curve to the data that's small, so you get a little bit more variability. But that would be kind of modifications for smaller things. And people who work on Bootstrap and theory and math of it and how to do it more efficiently in hard cases would do more complicated things. Right? But anyway, this gets a Bootstrap sample, right? And then so we can estimate the standard error of x bar, original x bar, not the x bar stars, by the standard deviation of the x bar stars, multiple ones. Right? We have a bunch of those. So the standard error of x bar from the Bootstrap is we're going to add up the x bar stars, the little E index there. Take the average of those, double average because it's an average of averages, and square that. Divide that by the number of times, number of replications we have, the number of simulations. This little b would go over all the different bootstrap times we've done it, and just take the square root of those things. So the standard error in the normal case, right, this thing, we're looking for something like square root of n, sigma over the square root of n. But we don't know sigma. We don't know that it would be exactly this formula. We don't necessarily have to be limited to x bar. So that's what we'd like, something like this, and this is give us an estimate that we can use. Yeah.
So it's like we're using two estimates to approximate the actual value?
Well, there'd be a so this is a.
Because aren't the x bar stars in kind of like an estimate of the estimate?
So it's, in a way. Yeah, so, I mean, you can make the analogy that the average in our pseudo populations, the artificial ones, is x bar. And now we're taking samples from that, and we're making kind of a, how accurate would our x bar stars be to estimate that x bar. So there's a parallel. But this is a computational, right? It's modern in that sense of using the computer power to overcome a lot of mathematical analytics, right? But it's trying to do a lot of the same thing. So let's look at some examples. And then we can return to some of these details to see if there's questions that generate out of that. Does everybody have a copy of the handout? So I took some examples from DeVore's, J. DeVore's book, J. DeVore's at Cal State Poly, San Luis Obispo. They actually have a fairly large undergraduate statistics department there and have for years. They did a book on probability and statistics for engineers and scientists that we used for the Statistics 220 last year. Right? And one of his examples is about taking an asphalt mixture and then having a certain area that's getting filled in, and like what percent of the area gets filled in. Right? So engineering, scientific applications like that can do that, and so that's one of their things. And it's a table with, let's see now, this one. It's just a text file. It's an example, so it's a percentage, and then some numbers there. The percentage of something that's being filled in. So there's air gaps and other things that don't get filled in, so it's not 100%. But you can compare this to other things. So that type of thing, read.table is a different reading command that will read in that type of thing. It's not comma separated, so it's just a text file, like ASCII text. Right? And it has put everything into a data frame that has one column, so if you actually click on that, right, it's one column. And it didn't quite like, the name that was given up there. It didn't reading into R, so we just called it X something. Right? I just want those numbers. So I want to strip off the structure and have a list of numbers to work with. Right? So this thing, I tried to just make it numeric, but it said, no, this thing's a list, it has more structure. So I can change it into a flat matrix that has no extra things and then make it numeric. That's just kind of geeky art stuff for making it work, right? That's one way to do it. So now percent is just a list of numbers. So here's the percents. Those are the different percents, right? Here's the histogram of what these data values look like. Right? So in this, right, in inference, these are the data values, right? They range from about 60 up to 85. There's all these individual values. That's the range, and there's a standard deviation for those. Right? The average in here about 73. But now we want to make a confidence interval that not of these, according how many, the length of that,
57.
yeah, 52 actually. 52 of them, yeah, up to 52 here. And so not that we don't care about just these 52, but if you use this out on the highways and roads 10,000, 100,000 times, what would be the average percent? Right? What's the ranges for it? Right? The average is probably not going to be down to 60. It's probably not going to be up to 85. Right? That's the ranges of the data. But what the average is something else. So we're going to do bootstraps. Let's do 1,000 times. Set up a something to hold all the bootstrap averages, and then you just do this leap. Right. I'm going to sample from the thing I call percentages, those 52. And in is 52. Kind of like to use symbols instead of typing 52 again. It helps reuse code. And I'm doing replace equals true, right? So that tells it to do it with replacement so that it can resample from the things, right? And I'm going to take the average of each one of those, and that's going to store as one bootstrap place. Run all that. Here's the set that up, and then run it. These are the histograms of 1,000 averages. So in the pseudo-population picture, you get all these different averages coming out of that. Right? Each of these is an average based on 52, and so there it is, about 71 to 77 approximately, right? As the ranges. Right. So this, if instead of taking samples, bootstrap samples, if I really could have been able to take different samples of size 52, do 52 on this day, and 52 on this day, 52 over here, you know, that the averages on each of those separate days might have had a distribution like this, somewhat pretty close, right? And so I'm going to just take the standard deviation of these. So the standard deviations of a variable, you know, this is about 4 standard deviations across, maybe 5, maybe 6, something like that. But if it's 4, kind of 72, so it'd be about, you know, about 1 or a little bit more. The standard deviation of those bootstrap samples is actually 0.87. A little bit less than I was kind of estimating there, right? And so my confidence interval is going to be the average, like the x bar minus about 1.6 times that standard error, standard deviation of the bootstrap sample, and the mean plus 1.96, kind of mimicking what I had in that normal example. Right? And so if I run that, it gives me about 72 up to about 75.6 as my average percentages. Right? So I'm 95% confident. I don't say there's 95% probability that that's where it is. It's not exactly that type of statement. It's 95% confident that the interval actually covers. Right? The slight phrasing difference is, you know, the view that the interval's random because I get a random sample, and that determines where it goes. But the chemical procedural average that you would really get by doing it millions of times would be somewhere out there. And we're 95% confident it's in this interval. Maybe the question is, do you achieve 75%? Well, you might achieve 75%. It might be, do you achieve 70%? Yeah, you're really sure that you achieve 70% on average. 75% is plausible, but kind of on the outer thing. Do you achieve 80%? No, you don't achieve 80%. Right? So it gives you an idea where it is. Now the t-test procedure is the one that we'll see in chapter 8 where all that comes from. But it also gives an interval based on the normal theory. And it's pretty close, right? It's very close to that, right? And this one has, you know, ours has some simulation error. So if you did a different 1,000 or a different 10,000, you know, increasing the number of bootstrap samples isn't going to move these intervals very much because it's dependent on the 52 sample size. Right?
Because you increased your 52 sample size?
Yeah, if you increase 52 sample size, then standard error goes down, like sigma over square root n.
Yeah.
If you had 500, right, then this thing would all be
Narrow.
shrunk down. Right? But if you do 100,000 bootstrap samples, this might be 75.56, right? That doesn't change the standard error of X bar based on 52. But it's pretty close. Right? So that's one example. That one's kind of straightforward. We'll have a bunch of ways of doing confidence intervals for that type of sample. It wasn't too, the data itself, right? It's not too skewed, no big outliers, nothing's down at 1%. And, you don't get 110% and have that asphalt spilling all over the place or anything like that. So it's not symmetric exactly, but it's not too asymmetric. Okay, so the second example from this book was the time to breakdown of an insulating fluid between electrodes at a particular voltage. At St. Louis Obispo, I think statistics is within their College of Engineering, Computer Sciences. So the statistician, the number of people is a kind of high engineering. So ready source of a bunch of
Experimental data.
Yep, data like this, right? And so these were just listed in the book. They weren't in any type of file, right? So for a smaller sample, you can just put them in, type them in, and it doesn't take more than a few minutes, and then check it, right? So initially I had an error. I had 44 here instead of 33, but there were some summary statistics in the book, right? So I compute the average and look at this. Oh, it's too high, and then look back through and find, okay, it looks like it's the right numbers. Well, I believe these are I don't know if these are in seconds. I don't recall what it said. But anyway, that, we'll just get it in there. And then time is just a little vector that's in there. Here's the histogram of time. It's a little bit more skewed, right? And the mean is 55.7. There are a total of 10 of these. Right? So this one is skewed. The book talks about it as being an exponential waiting time, kind of an exponential distribution, probability distribution. Our book often uses exponential, so it's kind of a skewed distribution that fits that. Right? We could do a confidence interval. So these are individual values, right? The average around here at 55, where is it? Is it 50, 60, 45? What are reasonable values for the average? So we can do a bootstrap for that. Again, it's just change the time name in there because it's a different data set. I didn't set up B or the bootstrap. I'm just reusing some of those overriding it. New length of n, sample with replacement. Run that. Here's the bootstrap samples. Still a little bit of skewness, I guess, right in there. The standard deviation of those is 20.5, right? So on a wider scale, 20 to 140. The original waiting times, 0 to 250. So that our data, what we really measure, the times, have that great variability and skewness. The averages from our pseudo population are more symmetric, not totally because of the tail up there, and they're narrower because of that. The standard deviation of the bootstraps is about 20, right? So 20, 40, 60, 80, 100. So about 5 standard deviations covering a lot of the averages there. And again, we can use that same thing to do that interval, right? So a 95% confidence interval for the average waiting time is somewhere between 15 and 95. That doesn't seem too precise. 10 trials doesn't really tell you too much, right? Maybe you need 40. If you had 40, right, then, because that square root of n, you don't make it 4 times, 1/4, you make it half, right? Because t-test, the intervals are a little bit different. It's like a little shifted, right? A little bit different. In there.
But still pretty wide.
Still pretty wide. A different way of doing intervals that we'll do more with on Wednesday is to actually use the bootstrap X bars themselves and look at the percentiles where they fall. And that becomes a bootstrap percentile idea for getting the intervals. So we have, right, we have our population. Right. We have our x's, and we get our x bars. We set up our bootstrap population. We sample, right, with replacement from our data. And that's how we're going to generate the bootstrap samples. And we do that once, and we get a x bar star. We do it again. And then we get a bunch of these bootstrap samples at x bars. And then we'll get a histogram of these things. And x bar is going to be pretty close to the center, typically. Right? But a different way of getting an interval for that would be to take a point here and a point here. This is the distribution of x bar stars that's in there. And so we choose a value here and a value here that leaves about 95% in the middle. Right? So if this would be the 2.5th percentile. And then this one up here, this value here, is the 97.5th percentile. And just use those points to get an interval, right? Kind of a seemingly another fairly straightforward way to go about that. And so if this simulation from the bootstrap population is capturing the essential characteristics of of a bunch of random samples there, we would think that the x bars would be kind of very similar to those. Yes?
In your examples, is there a reason you used 1,000 for the number of bootstrap samples?
Well, I think 1,000 is about enough. Yeah. So no, I was at Stanford for a year as right after getting a PhD, just as a visiting assistant professor. Brad Efron was there and has been there, and he's the one who wrote the theoretical papers in the 60s. So, you know, if you look at things like probability annals of statistics, it's rare to get articles over 10 pages. And here you would have a 60-page paper, like half a book or something, in this theoretical journal describing this. And he thought 200 would be fine, right? And with computers you can do more. And what you're doing is just trying to approximate a distribution, right? And so 1,000, 10,000 is probably enough accuracy to say where these things are, right? And for most things, I don't really want to think of this as that I'm exactly, the end point of that interval is kind of describing where I think mu is. And there's so many things in reality and the sampling process and things that can make a little distortion that I at least want to know the distribution to 2, maybe 3 decimal places. I don't necessarily want to know it to 6 decimal places. So there's a limit by which it's not necessarily needed. But 1,000, 10,000 for things. I see a lot of statistical papers where they're evaluating very complex statistical procedures, right? So they're doing something that's highly computational to analyze data in the first place, building this very flexible statistical model, and it takes them a lot of computing. And they'll do 100 simulations to give a comparison, right? And then they're reporting something to 2 or 3 decimal places. Well, based on 100 simulations, how do you know something so precise? So there's a trade-off. 1,000 gives you, I think, reasonable accuracy for most things. If I was doing something and the computer could run fast and I had some consequence, I might do 10,000. But much more than that is a little bit overkill. There's nothing wrong with doing 100,000 or 1 million, but it's not going to qualitatively change your answer too much. The center is not going to move. It's like the tails will wiggle a little bit as you do more simulation. I also like checking other ways of knowing, right? So I would probably look at, the t-test intervals. It's kind of the same. This is there's a function in R called quantile. And remember, my boot here contains the 1,000 means, right? So this will give me the 2.5% and the 97.5% from that distribution, right? And so that's 21 up to 101. So it's a little bit different than these. It's a little bit higher, right? And it's a little bit asymmetric around where X bar is. And it kind of reflects more of this shape a little bit more than saying taking the average plus or minus and making it symmetric. So it adapts. But so there's a little bit of uncertainty there. It's only 10 observations, so the three things give a slightly different interval. Where is the average? I'd probably recommend doing another 30 or 40 samples to know better. Right?
But if that's all the data you got.
If that's all you have, and you want to make sure that the average is below 100, right, or something like that, that's about all you can tell. The bootstrap then is used for another thing. So, in estimation of that probability distribution, not from this one, but going back to this one, the exponential, there's a parameter lambda, and it turns out the estimate is 1 over x bar, right? So that becomes our statistic. So in this, so an exponential model, that lambda is the parameter that governs the shape, governs how fast. The probability model kind of goes down like this for values of x, and how fast it goes down depends on lambda. The estimate of lambda that is used is 1 over x bar. Right. And it's not as easy to get the standard error for 1 over x bar. It's not 1 over the standard deviation because it's a nonlinear function, and so it's a little more complex. But Bootstrap, we can take Bootstrap samples, and for each Bootstrap sample, calculate x bar and take 1 over. And we can get several lambda hats, several estimates from a Bootstrap sample very fast. Right? And so we can still use the standard error, standard deviation of the Bootstrap estimates, right? Or just the percentiles, the quantiles, of those things from Bootstrap samples and get a confidence interval for lambda. And we don't have to know sigma over square root of n as a general formula. Thank you. So in this one, so 1 over the mean time is a lambda estimate of 0.018, right, as that estimate. So we want a 95% confidence interval for that one. And so if we take a Bootstrap sample, this takes a Bootstrap sample in there. And we're going to take the average of those values and just take 1 over it. Right? So we do that 1,000 times. And here's the histogram of my Bootstrap samples. Right? The standard deviation of those is 0.104. If I take plus or minus 1.96, it happens to go negative. Now, the lambda parameter has to be positive, so you probably truncated at 0 up to some point there. Or you'd use the quantiles. If you use the quantiles, you get 0.009 and 0.049. So you get 95% confidence for this other thing that's a nonlinear function of the data. So Bootstrap can be adapted to all sorts of different things. It works well if it's a smooth function of the mean, like 1 over the mean. There's calculus differentiability things that make it work out well. Right? In any case. There's just one more example along the same lines from the book. But before we go on that, are there questions on this example with the lambda? You could write out the, you get data, x1, x2, up to xn. For my estimator, lambda hat is going to be 1 over x bar. for the bootstrap. We're going to sample from, this is repeating a little bit of what we had before, but in this context, x1, x2 with replacement n times. And that will give us a bootstrap sample. I'll just write x1 star, x2 star, up to xn star. And then I'm going to take the average of those. And my lambda hat, say call it lambda hat star, is going to be 1 over that bootstrap mean. And so I do this whole thing, a large number of times. That's where I get all my different lambda stars. And then I take the central 95% of those to get my interval. Yeah.
So bootstrapping is kind of like permutation testing without assuming the null hypothesis?
Yeah, so it has kind of that analogy to that, right? So we didn't make these things have a mean 0 or a particular mean or match a null hypothesis, right? But it's just generating from the sampling distribution, and then the hypothesis testing, you have to do something to force it to match the null hypothesis, right? So if we said that the average was 5 or 1/5 or something, right, we would have to do something to make it match that. And these could be called kind of a non-parametric bootstrap in the sense that we're just sampling from the original data without any assumptions. If we thought that it was really exponential and the exponential parameter should be 5, right, or 1/5, right, we could sample from that distribution. We would just be simulating, right, and then get an idea. But there's other ways to do it to conform to different ideas. But yeah, that was this one. The last one that's on there. Oops, I had it, there it is a different example. This one, measurements of AGT level in micrograms in adults with chronic kidney disease. Urinary AGT levels measured in micrograms. This data also is just in a text file. This book provided some of the data sets that are a little bit larger. So AGT, and here's the values that are there. So when I read that in to R, it sets it up as 40 observations in a column. So AGT is just all in a column here. I don't really want that. I just want the numbers in the first column. So a second way of pulling that off is just to reassign just the first column and call that AGT. So that strips off the matrix structure. Now I just have a list of numbers. So those values are skewed. Right? A lot of the individuals, the adults, have smaller values, but a few individuals with a chronic kidney disease have much higher values. Right? And so these are the warning one, the alerts. There are more chronic cases, something that the average of those is 201. There are 40 values that are there. So if I want to do 95% confidence interval for the average, the average 201 was about here. These are the individual data points. The average for the mean is probably somewhere in this range, right? And so how close is it to my observed 201? Right? So this emphasis of data versus the average, and which picture shows the data, which picture shows the distribution of the averages is kind of a major concept. It's embodied in the sampling distribution versus the data, and then it shows up here. So if we do that simulation, right, that's it. The bootstrap histogram looks like that. It looks pretty symmetric. More so than the previous one with survival times. So if we run standard deviation of those, 39. So this would be the standard error for X bar approximately. Right, so our intervals look something like this, 124 up to 278. And there's a p-test confidence interval. And the percentiles, they're all pretty close in line. I did it, I went through twice, right? It's a little shifted. The intervals are a little shifted from the t-test, but they're not grossly different. Now, what if one way to deal with skew data is to take the square root or maybe the log. Right? If you take the log of the AGT, right, because this is kind of it's kind of like tens, hundreds, thousands, kind of that progression, and do a histogram on a log scale, it's not quite as skewed. It kind of goes the other way a little bit, but it's not as extreme. Right? So, and if you want the average on the log scale, 4.42, you could even exponentiate that to the mean AGT on the log scale. Oops. 83. So what is going on with that, right? So these are the original data. So if you take the logs and then take the average and then exponentiate it, it's not an inverse function because the way in order that it's done. I didn't really give all the code for that example. So you could look at your parameter that you could be. So we have some parameter like the average. And the estimator that we're going to use is E to the average on the log scale. Or E, this is like the log X bar for kind of shorthand. So it's a little more complex. Right, take the log and then take the average and then exponentiate that. And notice that it gave a smaller value. Right? It gave 83 instead of 201. Like the average before was 201, but that's really affected by those extremes. If you take the logs, it's more here in the center. Here's the logs, more here in the center for the average, and then exponentiate that, it end up being quite as extreme. Right? But you could bootstrap that. That doesn't bootstrap, I just did it on the average scale. But anyway, dealing with the original scale or the log scales, the bootstrap by using computing, right, allows you to do things that otherwise would have a little bit more complex analytics to figure it out. Right? So the big messages today are confidence intervals. Right? We want an interval to represent where we think the parameter is. Sometimes plus or minus, which is some real number line. We want it to be narrow. We want these things to have a high chance of coverage. Right? And the second thing is that instead of necessarily doing analytics and probability theory to get it done, we can do the simulation where we mimic the process of getting samples from the population. And if we can mimic getting 1,000 samples, we can just look at the standard deviation or the simple places where they lay out. And that gives us the interval. Right? So that's that. Yes.
Just a quick question. For part B1, about the cost, what should we do about that? There was another question.
Yeah, they're not raising yet, they answer it.
I was just wondering.
No. Do you have any thoughts about it?
Yeah,
Something else that you think would be?
Sure. Specific.
No, not in particular. There is a field of sports statistics that, all the teams have their experts to try and make predictions, things like that. And they follow, and they have to deal with factors like that. It becomes a challenging statistical problem, and you know, sometimes for statistics, oh, you're just doing sports, but there's going to be some complexity. So. Yeah. You have another class right before this one?
Yeah.
Yeah. So that's why I figured that you're just running over here to.
Yeah.
So that's fine. You know, I usually, if I have a handout, I'll set extra ones here.
Yeah.
And so if I start and you're just coming in, I just kind of start close to right when it, you know, turns time.
Yeah.
You know. But yeah, feel free to just grab it. And,
Definitely.
yeah, I know that's why you're coming in. So.
Yeah, I try not to do that. But
Yeah.
yeah.
But yeah. Cool. I don't know.